not all renewable materials are the same. If you're using wood for your project, inherently it's a more sustainable option. And that might not be always the case. Because when we are talking about renewability of a material, there are different factors that have been considered. And the broader impact of these materials on the ecosystem should also be considered. If it is a fast-growing plant or crop, then it has a higher renewable capacity. How much, carbon storing potential it has. Because to be honest, actually, our underwater plants like seaweed have much higher potential of capturing CO2 compared to our forest trees. So there are a lot of parameters that need to be considered when you are looking into nature or natural materials.
Before we go into the podcast, if you could just go and rate this show on whichever platform you're listening to it, it makes a huge difference to the podcast, the amazing conversations we get to have, and the incredible guests we're able to get on the podcast. So it's probably not something you would think about, but if you could just go rate the show, follow it, or share an episode, it does make a huge difference to the show. Thank you so much. In a world increasingly facing the challenges of climate change, with the Building Green podcast, we will dive deep into the intersection of architecture, design, urbanism, and environmental responsibility. I'm Ladina Schipf, your host. I've been an architect and building site manager for the past 10 years. During my studies at ETH in Switzerland, as well as in my working environment, I've had many touchpoints with sustainability, like many of you, I guess. I've also learned to question what I've been told, which is why I decided to go deeper into the topic and uncover what sustainability actually means. My mission is to highlight the transformative power of sustainable architecture, not just as a practice, but as a catalyst for broader societal change. Subscribe for more of our content and enjoy the show. Today, we're honored to have a true expert in sustainable material science, Gayatri Keskar, on the show. Gayatri's journey began with a passion for problem solving, which was nurtured growing up in an engineering family. With a PhD in material science and a career that spans startups and leading advisory roles, Gayatri has become a key figure in developing sustainable, high-impact solutions for the materials industry. In this episode, we talk about her innovative approach in evaluating sustainable materials, especially 3 material families that are often used in the construction process, which are leather and some of its alternatives, wood and concrete, where we talk about some common misconceptions about the materials and their circularity. Gayatri also shares her insights on the future of sustainable materials, including 3D printing, biodegradable materials, and the role of chemistry in shaping a more sustainable world. Gayatri's deep expertise bridges the gap between academic research and practical, scalable solutions in the consumer world and construction industry. I can't wait for you to hear her insights. Gayatri, thank you so much for being here with me today. It's a pleasure having you on the show.
It's awesome to be here. Thanks for inviting me.
So, Gayatri, let's start. Tell me your journey and how you got where you are today. What made you want to focus on material science and on sustainability?
Absolutely. Growing up in an engineering family, problem solving became second nature to me. When I was working on my last year engineering project at a national research lab back in my hometown in India, I was introduced to the nascent field of nanotechnology. And I was immediately drawn to it based on the potential it offers for transforming the material world. So it wasn't surprising to say that I decided to pursue my PhD in material science and engineering under a well-known scientist in carbon nanotubes at Clemson University. And when I was working on these new nanomaterials, I realized that they offer tremendous potential in terms of how they can achieve different functionalities, can solve different challenges that perhaps wasn't possible with traditional bulk materials. And this fascination continued even post my PhD work. When I joined a couple of startups, so I was very fortunate to have very early on experience in startup world. that made me more agile, more resourceful in my approach when using these next generation materials for solving high impact problems. But that fascination then was caught up with the realization that what's next? And certainly there was desire to extend my reach and relevance within the consumer goods sector. I was very fascinated to see how I can bring those great innovations to life that can transform everyday projects, everyday products. And that's what led me to a consulting and advisory role at Material Connection. There, I formally started working in the sustainability space, further building on my material science and product development expertise to empower startups and global corporations to develop purpose-built products, packaging, and experiences.
That's wonderful. So, can you walk me through your research process for evaluating new sustainable materials? Like, what are some of the methodologies you use and some of the requirements you look for when evaluating new materials?
Sustainability framework has evolved significantly in last few years. There has been recent focus on circularity and regenerative practices. Also, the tools and systems that are used for measuring life cycle analysis or product footprint overall have also become sophisticated because we have so many complexities based on our interconnectedness between the natural and engineered world, further layered with regional availability of resources, policies, regulations. So it's a tough cookie to crack, for sure. But one thing to keep in mind is we have much more robust framework now than before, looking into 16 different impact categories. But it's not always carbon, which seems to be certainly a dominating factor given any sustainability conversation. That might not be always the right North Star for a given application or given industry. For example, for transient applications like single-use packaging or fast fashion, the carbon footprint of individual product is significantly lower, especially if you think about the carbon footprint of like energy-based sector or transportation or construction. So what matters most is littering because there is no proper waste collection infrastructure in most of the countries, or especially in developing countries. And that leads to these materials entering into our water systems, into our landfills. And so the biggest concern is toxicity, ecotoxicity, water toxicity, whether they will be releasing toxic chemicals or unwanted substances and polluting our air, water, soil. And that becomes the major challenge is how you can apply green chemistry principles in order to make sure the products that you're creating are safe for people and for planet. Now, further moving down this spectrum to more durable and long-lasting products or sector like transportation, certainly carbon footprint matters a lot. But the criteria that you use in order to achieve sustainability is lightweighting because fuel efficiency is critical for this sector. And in order to achieve lightweighting, you move away from legacy materials, traditional materials that are used, such as metals, to more composites, mixing different materials together to achieve higher performance. And that way you can achieve high strength without adding more weight. So if you think about aerospace, if you think about automotive, there are a lot of composites that are used in today's vehicles compared to, even lightweight materials or metals like aluminum. It is used still in some parts, but mostly you're using now composites in order to drive that fuel efficiency. So it's a different lens that is applied in order to achieve similar end goal when it comes to sustainability. And then furthest away on this spectrum is, say, construction sector. Certainly, the kind of lifespan we're talking here is a lot longer compared to our everyday products or even cars, for say. And that's where carbon becomes a dominating factor, both the embodied carbon as well as the operational carbon. So a lot of recent developments are focused on lowering this carbon footprint, whether that is using recycled waste or whether that is using more optimized manufacturing processes. So depending upon your application and your industry, the impact category that is most influential can vary. And so does the approach or the material selection process that is used in order to achieve that.
So, Gayatri, I'm very curious to know more about a few material families. I've picked 3 material families that are often used in construction and design. One of them is nature-based materials like woods. Then we have leather and some of its innovative alternatives. And of course, concrete. So let's dive into wood first. What are the key characteristics that make wood a sustainable choice? Are there any controversies and misconceptions that you want to address?
So, by the way, great selection of materials. All these are iconic materials that are used in construction and design industries. So, starting with wood, one of the misconceptions that I would like to address here is not all renewable materials are the same. So, most of the times is considered that if you're using wood for your project, inherently it's a more sustainable option. And that might not be always the case. Because when we are talking about renewability of a material, there are different factors that have been considered. And the broader impact of these materials on the ecosystem should also be considered. Because certainly there has been a lot of work that is done in order to prevent deforestation, in order to preserve biodiversity, which is also becoming one of the integral conversation for impact categories. It also depends upon if it is a fast growing plant or crop, then it's certainly it has a higher renewable capacity, how much, carbon storing potential it has. Because to be honest, actually our underwater plants like seaweed have much higher potential of capturing CO2 compared to our forest trees. So there are a lot of parameters that need to be considered when you are looking into nature or natural materials. Some of the exciting developments in this category are certainly addressing this challenge is looking outside the traditional tree-based wood materials. So one company, Karoon, is actually transforming palm rattan into a highly engineered material. They're using energy efficient process because sometimes the manufacturing processes used are also quite energy intensive. And they are further harnessing the structural power of this material. The material itself has a very unique structure. It's actually porous structure. But the way they're transforming it is making it possible to achieve really complex 3D shapes, which are uncommon to find in wood material. So you can actually compression mold this material in order to achieve different shapes. Also, given the porous structure of the material, depending upon how you cut the material, whether it is along the direction or growth direction or across it, you can achieve interesting optical effects as well. So veneers are commonly used for its like as amazing surface material. So in this case as well, because of the porous structure, it can create that translucent effect. It can be used for backlighting. As well, it can, those like porous or the capillary that are seen in the porous structure can be used for different aesthetic and functional effects. So you can color it in a different way because of the way the pigments are absorbed through these porous structures. So it has a very inherent, interesting aesthetical interpretation that can be achieved through this material as well. You can also use it for different functional ingredients in order to achieve high strength without adding weight. So it's really amazing in terms of the kind of toughness and strength that can be achieved with this material as well. Moving further down, The another interesting area that we are seeing here is, again, using constituent materials of wood, that means cellulose and lignin, in order to create a composite. So lignin can be used as an adhesive or binder. So when you're using same constituents from the wood family in order to create composite, unlike traditional composites where you're mixing different materials, which make it really difficult to recycle these materials, the end of life is not necessarily well defined. Although there has been work done in order to reclaim these materials effectively, it's still not necessarily that mature technology. But with these recent developments, now it's possible to have composites, again, high strength, lightweight, but keeping the same material family. So it doesn't affect the intrinsic biodegradability of the material. And they can be used for various applications. Again, something that requires really high performance in, say, snowboards, skateboards, in automotive. It can be 3D printed. So it offers a wide range of possibilities in terms of how the material can be used. And then the last one in this category that I wanted to talk about was MDF, medium density fiberboard, which is again widely used in construction industry. And there have been already ongoing efforts in order to use recycled input. So the recycled paper is coming from, paper and pulp industry. Most of the times it's using, again, tree trailings. And what we have started seeing is also use of wheat straw and rice straw. So agricultural waste that is used for fibers in this MDF composition. And another recent development, which is bringing back the conversation of green chemistry, is using bioresin. So far, the industry standard has been using formaldehyde-free resins that still has isocyanate, but with isocyanate. So with this, the recent development, now companies are exploring plant-based options. So using rapeseed oil or sunflower oil, they're able to create a 100% bio-based composition for MDF that will still give the same performance. And although it's not technically recyclable yet, but given its green chemistry, that's an absolute must in order to create new products to make them circular. Having safe materials in your chemistry is so important. And so this is a step in the right direction in order to move towards circularity.
That's fascinating. Have you ever worked with hemp?
Yes. So hemp is also another interesting fiber that has been used very widely for construction. Again, sometimes it is combined with plywood or some of the traditional substrates. Sometimes it's used on its own. It has also been used in other materials that when you talked about concrete. So it's also been used in those compositions as well. So it's a very universal material, especially given the properties that it offer, and it used in a wide range of applications. Anything from acoustic insulation, anywhere you will use fibrous materials, all the way to, as I said, like concrete, as well as in particle boards. So definitely a really interesting area to explore for alternative fibers.
It's interesting. Yeah, I had a podcast guest a few weeks ago, and they were at that moment planning, I think like 40 housing units with hemp. Super interesting. So do you have like a rule of thumb in construction when you recommend using wood for structural parts?
So it depends upon obviously the performance requirements where it is used. It also depends upon the available resources. So as I said, like hemp is not necessarily available in every part of the world. So sometimes that's why we have started seeing more local innovations coming to play based on what are the available resources. So when I said like wheat straw, rice straw, these are companies that are tapping into their locally available waste streams. So it's very important to keep in mind that the resources, especially the alternative materials that are you looking into, are locally available. And so it will be dictated by the availability, it will be dictated by the functional requirements for a specific application. Again, given recent advances in our processing technologies, like 3D printing is also widely being used in construction. So it will also depend upon what kind of processing technique you're using in order to achieve the structures that you're creating. And that could also lend itself to the conversation of what materials you can use.
Makes total sense. And for interior design, leather is often debated in terms of sustainability. Can you discuss its biodegradability and how it compares to some of its alternative materials in terms of environmental impact?
Certainly. Leather has become a very polarized topic in recent years because there have been so many different parameters that are important to this conversation. So, leather is not typically, but traditionally been considered as, animal skin, so directly derived from animal hides. And it's such a amazing material because it offers a wide range of properties that could be um, really promising for different applications. So it has natural stretch, it has, weather resistance, because obviously animals, they roam around in extreme environments. So certainly that is embedded into the material itself. It has this natural patinas, the texture of it. So there are so many interesting aspects of the material that are often overlooked when we are talking about finding alternatives, because it's unimaginable to find a single material that is going to mimic each and every characteristic of natural leather. And that's where we come to like different generations or categories that have been offered in recent years as alternatives to leather. So the first generation was synthetic leather. Whether it was using PU or PVC, it was 100% plastic based. And it was developed as an affordable alternative. It was also claimed as vegan leather. I don't necessarily want to get into all those nomenclatures because it's always very confusing. But certainly, given the fact that it was not derived from animal, made it vegan alternative. And it was pretty much focused on trying to mimic the texture that you will find in leather and the performance. But in general, even with the traditional leather, one of the challenges is the processing of leather involves very harsh chemicals throughout the entire process. So there are different steps involved, like preparing these hides, pre-tanning, tanning, finishing. And at every stage of this process, heavy chemicals, metals are used in order to achieve the right performance characteristics. So sometimes even natural leather can end up into a product that is not biodegradable because it's so heavily transformed through this, chemical processing. So one of the school of thoughts is, given that we are or we haven't yet stopped eating meat, because leather is traditionally been considered as a side product or byproduct of the food industry. Although there have been exceptions, but that's primarily where the hides are coming from. So if we are not going to stop eating meat, is it ideal use of like that leftover skin to go to landfill or like compost it? If it doesn't end up in the right environment, it can again create methane and some of the other challenges which are even more potent than CO2. Or does it make sense to actually maximize the potential of this resource by converting it into leather? So let's just put a hold on this. But this is one thought that we are seeing, and companies are actively working on optimizing the processing of leather. As I said before, it is heavily influenced by different chemicals. So companies are looking into ways in order to dial down the chemical intake and make it much more chemistry wise safe, so that way it will preserve the biodegradability of the leather. And that's where the second kind of concern arises. Is leather is a material that is known for its high quality, for its endurance. It is kind of a material that will be passed on from one generation to other generation. And so is it a fair comparison, or is it a fair indicator to have biodegradability as a predominant factor in designing this material? Or should the focus be more on making the material highly durable, high quality, so it will last as long as possible? And I will come back to that, why that's important.
And there, it's also the responsibility of the designers to make responsible use of it and design something that is really long lasting also, like in terms of style.
Definitely, because durability has multiple aspects or dimensions to it. One is physical, which is coming from the performance of the material. The other one is emotional, which is about how you can make that product stay relevant over time. And that's through how it's been designed, what kind of styles, whether it's classic, seasonless. And I feel like some of the intrinsic characteristics of leather makes the material really exciting, irrespective of like seasons, irrespective of the design as well. But then there are different requirements when this material is used for different applications. So we talked about, fashion being one of them. The other one is using it as a surface material, and that can be for automotive, that can be for interior design. And based on the environment that it is used or applied to, raises questions in terms of what kind of performance you should be looking for. Because especially if you're using this material in automotive, then you're looking for a surface material that is easy to clean. So that will require a high degree of abrasion resistance, that will require a high degree of water resistance. Versus if you're using it for like interior design, how the material flows and folds. So the flexibility is going to be a lot more important. So there are different aspects that would become more significant for a specific application. And that's why, as I said before, it's difficult to find an alternative that's going to meet all your requirements, that's going to give the performance that exactly mimics how it looks and feels like leather and also performs like leather. And that brings us to the second generation or second category of leather alternatives, which is hybrid. So in this, basically, there is a architecture or structure where you have sort of three different layers. You have your backing, which could be coming from natural fibers or synthetic fibers. Then the middle or the core layer is where most of the innovation takes place in terms of using agricultural waste or any fibrous waste. So we have started seeing use of, pineapple fibers, cactus, apple. So many different, fruit residues are used in order to create this core layer. And the top layer is what gives its final sort of performance and finish. So in order to make it last longer, durable, having water resistance, PU coating is most commonly used in order to provide. It also helps with, creating different textures that you're looking for when you're trying to mimic the look and feel of leather. There has been more advancements made recently in order to have partially this PU coming from biomass, but still the end of life is not well defined for this material. It's not biodegradable because of different materials that are mixed together.
If you're enjoying the show, I have a small favor to ask that would mean the world to me. By rating and sharing the podcast, you're helping us grow and spreading our mission of making sustainability really desirable and cool to a wider audience. Besides of that, imagine impressing your colleagues with the latest insights on sustainable architecture. So make sure you follow the podcast and become the most informed in the room. Thank you so much for your support. Tell me more about how fruit can become leather. What does that process look like? Do you know?
So most of the times what is done is actually it creates in sort of a puree form. So it is dried and then compressed into a sheet that is used as a core layer. So you will have your fruit residue that's sometimes mixed with other ingredients, keeping within the plant family in order to provide it specific characteristics. And some of these are really interesting ways to achieve not just upcycle fruit waste, but also achieve interesting characteristics for the end product as well. But given its multi-layered construction and use of PU historically in order to achieve that final performance and finish makes it challenging. But there have been really interesting products on the market currently using pineapple, using cactus, sometimes using even mushroom. Again, companies are tapping into local available waste streams and how they can be repurposed in order to create this core layer. For some applications, perhaps you might not necessarily need the top layer, but most of the times you will require some sort of top finish in order to protect the material if it's going to be exposed to outside or different environmental conditions. And then the last category is plastic-free leather. And that's where the real innovation is happening in terms of how you can tweak the chemistry. So there are different examples on the market in this category as well. Most of them are still in the early stages, but there have been few companies that have made a headway and reached market. One of them being natural fiber welding, where they are using natural rubber and then combining it with plant-based fibers like agricultural waste, natural minerals, and pigments. So it doesn't necessarily go through the traditional dyeing process. There is no water used during the processing of the material, and giving it a very unique and distinct look and feel. So one thing I wanted to clarify here is when we are talking about this specific category, it's a totally new class of materials. So although they are considered as an alternative to leather, I think they do a lot more. They go beyond leather because now it's possible to achieve materials that are translucent, which wasn't possible with natural leather. You're able to create performances that were not possible before as well. There have been companies working on using CV in order to create inherently fire retardant leather. So it's really interesting to see how these natural ingredients can be further optimized to achieve characteristics that take this new class of materials to the next level in terms of what can be achieved on the aesthetical level as well as on the performance level. We have started seeing using mycelium and actually growing new materials, like using biofabrication as a way of creating these new leather like materials. And one thing to point out here for this category is also because of these non-traditional way of making materials is giving you an opportunity to fine tune the properties or to tailor made this material for the end application. So now it's possible to have tunability by just controlling the growing parameters in case of mycelium to achieve different densities, to achieve different textures, in order to achieve different performances. And it's possible to not rely on BioPU or any other synthetic coating in order to perform in various environments.
Can you give some examples of what they could look like?
Mycoworks is a company that is currently working on mycelium-based leather that they call it Rishi, which is like fine mycelium. They have already collaborated with quite a few brands and have launched this material into accessories. They are also talking with automotive brands, India design brands. So it's possible that the material can be tailored for like various applications where traditionally natural leather would be used. But also interesting aspect about this is most of the times when we are talking about these new materials, it takes time to mature the technology. It takes time to scale up the production in order to make the technology commercially available. And sometimes during this process, because of lack of investment, funding, interest from companies, it becomes hard for these small companies to reach the market in a beyond just like, limited editions or small collections here and there. But MicroWorks has secured significant funding. So that's again encouraging to see that this sector is growing rapidly, but it has also got enough momentum in order to cross that bridge and be market ready.
Yeah, it's super interesting to hear how everybody is like innovating with these things. And so let's move towards concrete, a very contrasted material, which is also or even more essential in construction, but has a significant carbon footprint. How are the advancements in material science addressing the sustainability of concrete?
So, as you mentioned, certainly the carbon footprint of construction and especially concrete is quite significant. And it comes down to the sheer volume of the material is used globally. It's like 4 billion tons of concrete is used globally. And that causes 8% of GHG emissions coming from this sector. So these are like significant numbers. And that gives immense potential in order to find low carbon, low impact materials. So a lot of new developments are happening in this space where companies are looking into cement, the Portland cement that is traditionally used in concrete mix, how you can find alternatives that doesn't involve carbon in order to bring down the carbon footprint. So one approach is using different types of rocks. So basalt rock, where the chemical composition of the material is it's silicon, aluminum, and calcium. And so the cement is like calcium carbonate. And so rather than having to have carbon based source, they are using these rocks as a starting material. And then they are also focusing on using captured CO2 in order to transform this calcium into calcium carbonate. So rather than having to, or through the traditional process where it releases carbon dioxide, now you're capturing carbon dioxide in this process. And there have been different curing processes that are used in order to achieve that. They're using bionic CO2, so that is coming from, ethanol fermentation to make sure that you are actually further maximizing the impact of the positive impact, of this technology. So it's interesting way to see how companies have started looking into alternatives, both from the processing side as well as from the raw material or feedstock side, in order to reduce reliance on carbon-based or carbon-heavy starting materials. Another interesting way to look at it is also companies have started looking into, which was there to begin with, but it has definitely intensified in recent years, is finding alternative waste streams. So some of them are coming directly from construction debris that can be repurposed into that. And the recent work has also been how you can use or transform non-recyclable waste streams. So for example, gypsum drywall is not currently being recycled. So there has been work done at the university and the startup level in order to mix it, combine it with other waste streams such as cardboard, as well as waste-derived cementous binder to convert it into a material that can be brought back into the construction or design industry. So it's interesting to see how diverse we are in terms of exploring and exploiting these different waste streams to create raw material. And also going back to the processing, other interesting aspect which we briefly touched upon before was using 3D printing. That gives you an additional layer of environmental friendly attributes, because the process has already been optimized. Most of the times it's on demand. It significantly reduces the time that is required. So there are a lot of 3D printed homes that are already been designed, developed, and executed using different waste streams. But certainly that also gives you ability to start repurposing some of the construction debris, whether it is you're using stone powder, you are using again these cementless or non-traditional cement based concrete mixes as well. So there is a lot going on both on the material side, on the processing side, which is making concrete not to be seen as a carbon positive material, but more seen as a carbon neutral material in case of its overall footprint.
Can you elaborate on that a bit? That 3D printing is much more sustainable than just like the traditional way of using concrete.
So 3D printing, there are different, inherently, the method is much more sustainable because it's very resource optimized method. You are not creating any waste in the process because the designs are already being optimized based on how the structure should look like. You are exactly printing what it should be there. These methods also doesn't require any form work, or it doesn't need to go through the traditional way of curing. It's much more fast curing, so the time is also significantly reduced. Labor is significantly reduced. It's possible to do that much more locally, so you are not relying on transporting materials from different regions. So there are a lot of benefits of using 3D printing in terms of flexibility with kind of materials that can be used, as well as structures which traditionally wouldn't have been possible because may require a lot more reinforcement in order to achieve that. With 3D printing now, you can have much more topologically optimized structures that will also give you benefits in terms of using less material to begin with than the traditional structure.
Makes a lot of sense. And what materials are usually used for 3D printing?
We have seen a whole gamut of materials that are used for 3D printing, especially for construction. We have seen using, concrete mixes. We have seen using clay. Actually, that's also a really exciting example of using terracotta for 3D printing ocean-friendly structures that can be used to restore coral reefs. So we have also started seeing use of 3D printing for more restoring work. Just like stone can be used depending upon what 3D printing process you're using. Most of the times it creates sort of a paste. So you're adding this in the powder form, in the ink, or in the gel, and then it's 3D printed layer by layer. And so it gives you a lot more flexibility in terms of what materials can be used. Again, you can also rely on plastic, some of the other waste streams that are also commonly used for creating structures, and it will still give the same kind of performance because to begin with, plastic is over-engineered material, so it does have the performance. Unfortunately, that's the good thing and bad thing about that material is also that because it is such a highly engineered material that it doesn't necessarily make it easy when it comes to the end of life. And the plastic is also quite commonly used, like plastic waste is also quite commonly used. We have recently started seeing some of work in 3D printing glass as well. Again, it's still in the early stages, but glass can be 3D printed. Wood can be 3D printed as well. As I said, like when you are trying to come up with different formulations that are using cellulose and lignin. So it can mimic wood look and feel. So that's also another category, especially when it comes to natural materials. It's difficult to 3D print natural materials compared to some of the natural, in the sense, the bio-based materials are difficult to 3D print them, but we have certainly started seeing a lot more variations of, again, coming from the waste stream or just from the natural stream that can be used for 3D printing. I mean, metals as well, definitely, that can be 3D printed.
Do you think that's the future, that most buildings are going to be 3D printed?
That's a good question. I mean, 3D printing has a lot of advantages. It becomes a lot easier to do so, especially given it also reduces the cost, obviously, because as you are reducing the materials that are used, the time that is required to make it, so it is easy to create these structures. Whether that will take over the entire construction industry, I don't think necessarily we are there yet, but there are certainly specific applications that would be transformed, or we have already started seeing being transformed using 3D printing.
That's super interesting. I'm looking forward to seeing where this goes. And so, Gayatri, you often work as an advisor also for designers sometimes. What are like the biggest challenges you face when working with clients and when you try to push for more sustainable or innovative materials?
There are a few different challenges, especially given the recent focus on circularity. The challenge being now part of a puzzle that is really hard to control, which is end of life, which is post consumer waste that is created, is becoming a lot more important to this conversation in terms of closing the loop. And that requires, as we talked about previously, thoughtful design, education, and empowerment. So let's take a step back. Resource waste management hierarchy. Perhaps you have heard about it. It started with the traditional 3 Rs. And in recent years, it has extended to, I guess, so now it's 9 Rs or 11 Rs. So it's really interesting to apply, to see how it's extended, making it relevant given other conversations in the space, but also crucial to apply this when you are designing new products. So these current 9 Rs are rethink, refuse, reduce, reuse, repair, repurpose, refurbish or remanufacture, recycle, and recover. And if you think along those lines, following those hierarchy, there is a serious research and work been done in order to put in place like why we are following this hierarchy. And if you follow that rationale, it is going to help us with creating more circular products, more circular business models. And that's where the design phase plays such a huge role. And especially material driven design is critical to this conversation to make sure that we are able to enable these circular business models. And that's where the consumer education and empowerment is equally important. Because if the products are not designed properly so they can be easily disassembled for repairing, for remanufacturing, as well as just clear for end users to know exactly what they should be doing at the end of life, as well as at the end of use, then it becomes easier to keep these products in use as long as possible, but also follow the circular journey that they end up in the right environment if it needs to be composted, if it end up in the right bin, if it needs to be recycled. So the material recovery becomes a lot more efficient. And for that, we need to everyone along the supply chain to do their part, but especially the end user who will be driving these journeys need to be in a position to do the right thing.
Yeah. Can you debunk one common myth related to sustainable materials that people often think is something sustainable?
So most of the times, and again, there are a lot more nuances, so I don't necessarily want to oversimplify this, but most of the times people think if they see that recycling symbol on the package or on the product, that means the product will get recycled. In theory, yes, but there are so many different layers to that conversation. Because as I said, like it finally comes down to the available infrastructure. So even though the material can be recycled, the product can be recycled, if you don't have the right infrastructure in your region, in your municipality, then it's not going to get recycled. Just because the material is recyclable doesn't mean that it will get recycled. And so that's why having the collaboration along the entire supply chain, not just with upstream partners who are working on creating these products, but also downstream partners to make sure that you have right infrastructure or you're creating products that are going to be supporting the existing infrastructure in that region. And I know that becomes a lot more difficult, especially if you are a global brand. It is harder for you to create more regional products just to satisfy the regional uh, recycling requirements or based on the available infrastructure. And that's where we are seeing is global brands sort of suffering because there is no standardization when it comes to Even recycling, this terminology is not standard. There are so many different layers to it. When you say recycling, is it like material to material recycling? Is it material to feedstock recycling? It's material to. So there are so many different layers and nuances. Because, for example, in Europe, what is considered as recycling is not necessarily the same what's considered in North America. So that's why the infrastructure, the overall ecosystem available to support that end of life is equally important to be considered when designing that product.
That's kind of mind blowing. I've never thought about the definition of recycling. And the fact that you're telling me that different countries have different definitions is really, really mind blowing.
Not the definitions, but the implementation strategies are quite different. Like recycling material to feedstock, like for example, is very common in Europe, but it might not be considered as a um, actual sustainable way of recycling materials. Most of the times we tend to rely heavily on material to material recycling, which is most logical thing to do. If you're following, Ellen MacArthur Foundation work that has been in terms of explaining this framework that is around recycling, you want to keep the material as close to the final use as possible in order to, because as you go further along, or further away from the final use, it takes a lot more resources to bring it back. So if you are recycling your end product into feedstocks, it is going to require a lot more energy in order to convert it into a material and then into a product to bring it back to the market. As opposed to that, if you are, and that's where mechanical recycling versus advanced recycling. Again, let's not go into that conversation, but there are so many nuances to this conversation, and it becomes a lot more challenging to implement it on a local level, given the lack of standardization.
That's super interesting. Gayatri, I have one last question for you. What's the most exciting material discovery you've made in your career?
So I briefly mentioned about carbon nanotubes during my intro. And that was work that came out of my thesis at Clemson University. So I developed a patented process to produce doped carbon nanotubes, single wall carbon nanotube to be precise. And what was exciting about that work is not just the technical complexity of the project, but it was in collaboration with IBM. So I was pretty excited to witness and experience firsthand the convergence of academic research and industrial innovation. And it was a much challenging problem to solve at that time, given a very less research was done in this area, and because of, again, the technical challenges in terms of achieving. So the end goal was to create field effect transistors, so one of the electronic component using carbon nanotube. And so for people who don't know what carbon nanotube is, basically it's a single layer of carbon atoms that has been rolled to form a tube. And being on a nanometer scale, so again, to provide some context, basically the width of hair is 80 to 100,000 nanometers. So you're talking about really minuscule level. And that gives it very distinct and useful properties that can be explored for a wide range of applications. So my work was more focused on electronic components. Again, with carbon nanotubes, we can realize quantum computing, but it's also a material that can be used for self-sensing concrete, that can be used for de-icing roads. So it's like really interesting additive that can be used in a wide range of applications. And another interesting anecdote for that is actually recently accepted strategic advisory role for a startup called Cecilia, who's working, and it was kind of a full circle moment for me because they are bringing carbon nanotubes back with a modern twist. So what they're doing is they are actually upcycling plastic waste using modular microwave-based process to convert it into hydrogen and carbon nanotubes. So it's very exciting to see how companies have taken it to the next level, that the material itself has very interesting set of properties, but traditionally it was a very resource intensive process to make carbon nanotubes. They were made in labs using very sophisticated equipment, require very, as I said, high heat and higher level of control throughout the process. But now it's possible to use waste streams that are easily available to us. And the challenge with the carbon nanotube is, although it has been, it's not a new material, it was developed a while ago, is the cost associated with these advanced materials. It makes a lot harder for these materials to find applications. You always look for that niche application that is going to justify the cost. But now, thanks to these newer technologies, it's possible to produce carbon nanotubes at a fraction of a cost while having a sustainability story behind it, because now you're using waste stream and you're also creating hydrogen, which essentially can be used to power the technology. So it can have a carbon neutral profile compared to very intensive and sophisticated techniques that are currently being used. So that will open a lot of new applications for carbon nanotube, because now you are able to make it affordably and at scale.
That's super interesting. And just like in terms of the material applications, is there any specific application in construction or design for that?
So carbon nanotube, as I said, like in construction, it has been explored because of its impressive electrical and thermal conductivity. It's used as sensing for sensing applications. So it can be embedded into. It also provides superior performance through mechanical reinforcement. So that's the other reason carbon nanotube has been tried and tested in concrete, in order to improve the performance, but also in order to provide the conductivity. So in like new bridges and other structures that are being built, you want to have that auto sensing capability. So you are able to sense if there has been any fracture or, any adverse effect on the performance or on the structural stability. So that way you can respond to it. Sometimes there have been inbuilt solutions in order to resolve it if it is a minor change, or at least it will trigger an action if it needs to be resolved through external processes. But those sensing capabilities are now possible using, additives like carbon nanotube to make them smart, to make them intelligent in terms of how we can create our future structures and also make them more resilient.
That's super cool. Thank you so much, Gayatri, for all your insights and sharing all this knowledge. If our listeners want to follow your work, where can they find you?
LinkedIn would be the best way to get in touch with me. So Gayatri Keskar, if you just look me up, and feel free to reach out to me if you have any questions or want to further discuss on any of the topics we covered during this conversation. I really appreciate this opportunity to connect with your audience, and you've been doing amazing work in terms of bringing more visibility to these sort of complex, sticky problems.
Thank you very much, Gayatri. It's been a pleasure. A huge thank you for listening. Make sure you subscribe to the show wherever you listen to the podcast to support me and so you don't miss an episode. And while you're there, I'd also be so grateful if you could rate and review us. If you have any guest suggestions or any feedback, you can find me on the socials at @LadinaShip. Thanks.